Okay, we're going to do lesson 9.4, which is entitled Real Numbers. Now, up to this point, just about everything that we've worked on in this class has had to do with rational numbers, up until this chapter anyway. Rational numbers are numbers that typically can be written as a ratio, as a fraction. As a decimal, when you write a rational number as a decimal, it either terminates, it stops, or it repeats, like 0.2222222 and so on. Those are rational numbers. We now come across another whole set of numbers called irrational numbers. That's what we've been hitting with some of these square root numbers that we've been working with in this chapter. Irrational numbers are numbers that when you write them as a decimal, they cannot be written as a fraction. When you write them as a decimal, they neither terminate nor do they repeat. So, rational numbers and irrational numbers, those are the two. These two, when you bring them together, form, and here's the definition, the real numbers. A real number is a number that's either rational or irrational. Now again, rational numbers are the ones that we're used to. Rational numbers like 1/2, 0.7, -3. Those are all rational numbers. You can change any of those into fractions, or if you write them as decimals, they either terminate or they repeat. Okay? But irrational numbers, we're not as familiar with some of those, so I have a couple of examples over here. I created my own irrational number here. Now it looks like it repeats, but it doesn't repeat. Repeating means the same number or numbers going again and again and again. Here I have 1s and 2s, but it's not 1, 2, 1, 2, 1, 2, 1, 2, 1, 2 forever and ever and ever. It's 0.12, 1, 2, 2, 1, 2, 2, 2, and so on. There's a pattern, but it's not a repeating pattern. It's just that I add an extra 2 each time in between the 1s. This is considered an irrational number. The square root of 5 is considered an irrational number. I went ahead and punched it out on the calculator, and I put down several decimal places. But this would continue, it would go on forever and ever. That's why the 3 dots are there. But it does not repeat its values. 2.2360679 and so on. So a lot of these square roots that we'll be dealing with are irrational numbers also. Now the ones that come out evenly, like the square root of 4, that's equal to 2, that's a rational number. The most famous of all irrational numbers is, of course, pi. Pi, remember, is approximately 3.14, but that's an approximate. It has, like the square root of 5, it goes on forever. If you write it as a decimal, it does not repeat its values. 3.14159 and so on and so on and so on. I know students that have dozens of the digits memorized, but in this case, take my word for it, punch it into your calculator. If you have that type of a scientific calculator, you'll get about 7 or 8 decimal places, and the pattern will not repeat. So this is an irrational number. So remember, if we take the rationals and the irrationals, we combine them, we get the real numbers, and that's what this diagram is going to show you here. This big circle is to represent the real numbers. Rational numbers, irrational numbers, and of course, with rational numbers, you have the whole numbers, right? As part of a subset of the rational numbers. The whole numbers 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, and so on. Of course, an even bigger set would be the integers. We use the capital Z for integers. They include the whole numbers, but they also have their opposites. And that's also a subset of the rational numbers. So maybe it's kind of a way to picture what's going on here. Rational numbers, remember, we can write them as fractions. If we write them as a decimal, they either terminate or they repeat. Irrational numbers we cannot write as a fraction. And if we write it as a decimal, it will either, it will go on, it will not terminate first off, and it will not repeat. Neither non-terminating nor non-repeating there. All right, so let's try some examples. All right. Here we have an example where we're telling whether the number is going to be an irrational number or an irrational number. Remember, a rational number can be written as a fraction, so since this is written as a fraction, we know this is rational. Now this guy here, the square root of 2, 2 is not a perfect square. It does not come out to be evenly. In fact, if you punch it out on the calculator, this is approximately 1.414, but it goes on and on forever and ever. Non-terminating, non-repeating, this one is irrational. So you say, oh, if it has a square root sign, it's irrational. Well, not necessarily. The square root of 25 is exactly 5. And we know 5 can be written as a fraction. That's 5 over 1. So it's a rational number. So it all depends if the square root will simplify into a nice neat number or not, like an integer like 5. Can't always just base it on the fact it's a square root, therefore it's irrational. Now to work the next couple of problems out, you really need to have your calculator close by. So I grab my calculator here, I punch it on, and I'm going to take the square root of 5. Now we had this written down before. This is approximately 2.236. And of course this is 11 divided by 4. If I divide 4 into 11 on my calculator, I get 2.75. We can compare decimal places much easier than looking at these numbers written in this form. This one is irrational, this is rational. But I can see that this is smaller than that, so I'm going to compare it with a less than symbol. Now over here, this is going to be the opposite of the square root of 8, or negative square root of 8. So this is negative, and I punch in, since 8 doesn't come out nice and neat and even, I punch in the square root of 8, and I get 2.828. 2.828. Now it keeps on going forever and ever and ever, but I just need enough to compare decimal-wise. And of course this is negative 5 over 2. If I divide 2 into 5, I get negative 2.5. So I can see here by the place value, remember these are negatives, so the bigger it looks, the smaller it's at. This is smaller than that, another less than sign. For the third example there, I'm certainly going to plug in the first expression on my calculator. So I'm going to take the square root of 2, which we already know is about 1.414. So I'm going to take that, and I'm going to multiply that times negative 3. And I get negative 4.2426. Now remember, this is negative 4.2. So this looks bigger than this. Remember, they're negative, so it's kind of the opposite of how it really looks. The bigger it looks, the smaller it actually is. So this is smaller than that, and that's a less than. Now I'm always worried when I write down examples where all the answers turn out to be the same. And in fact, all three of these turned out to be less than. It's because sometimes students think, oh, it's always a less than. It just depends on the numbers. It just happens that these three examples all came up that way. Now the next two examples say use a number line to order the numbers from least to greatest. Well, what I'm going to do here is I am going to write down an approximation of each of these numbers written as a decimal using my calculator. So this turns out to be negative 1.732. The square root of 7 turns out to be, let's see here, let's see if I can get that to work again. The square root of 7, good Lord, if I could push a button I'd be okay here. The square root of 7 is about 2.646. 21 divided by 8, that's going to be nice and neat, and 2.625. And then of course this is going to be, if I divide, negative 1.8 if I'm not mistaken. So negative 1.8 is further to the left than negative 1.732. So this is negative 9/5, and this is the negative square root of 3. And then the two positive numbers over here, well, let's see. This is just a little bit smaller. This is 2.625 and this is 2.646. So 21 over 8 and the square root of 7. And there are my numbers in order from least to greatest. This one first, then this one, then this one, then this one. And if it helps, you put commas in between. I used the number line just so that I could kind of keep everything checked in order. Over here, now these are all positives. So I'm just going to use my calculator on the ones I'm unsure of, like the square root of 10. The square root of 10 is 3.16, approximately. It's an irrational number. This is 2.33, and the 3's go on forever and ever. And of course, 2 times the square root of 2 should be about 2.8 it is. This is 2.828, and it goes on forever and ever and ever. So again, if I put these in order, these four numbers here, looking to see which is smallest, that would be the 2.33, so that's 7/3. And then the next one would be 2.828, so that's 2 square roots of 2. And then the next one would be 2.9, which of course is 2.9. And then the last one, 3.16, or the square root of 10. And again, from least to greatest, this one, then this one, then this one, then this one, in that order. All right? And I have them in order from least to greatest. I have one more example for you, and I'm going to do that next. Okay, the last problem is a story problem where we're going to deal with some irrational numbers here. Starting at their campsite, Kim and Tim, this is a tribute to two guys that I went to kindergarten with that were identical twins, Tim and Kim. Kim and Tim walk two separate trails that are each 500 feet long. Kim walks 400 feet east and then 100 feet south. Tim walks 200 feet south and then 300 feet east. Who is further from the campsite? From the campsite itself. So we'll start here with Kim. He walks, here's the campsite, he walks 400 feet this way, east, and then he walks 100 feet south, like this. So we want to know how far he is from the campsite. Looks like a right triangle. Looks like the Pythagorean theorem. I'll call this x. And I have x squared equals 100 squared plus 400 squared. 100 times 100 is 10,000. 400 times 400 is 16 with 4 zeros, so that is 160,000. So that's 170,000. So I'm going to need my calculator here because I'm going to take the square root of this, and again, not plus or minus here because we're only looking for the positive square root since it's a distance, and I get the square root of 170,000 to be 412.31, and it goes on and on forever and ever and ever, and this would be in feet, so this is an approximate. Now we have Tim. Tim walks 200 feet south from the campsite and then 300 feet east. So here he is at the campsite. He walks 200 feet south and then he walks 300 feet east. And we want this distance from the campsite. So again, I'll call this one y here. And I get 200 squared plus 300 squared is equal to y squared. That's another right triangle, and I'm using the Pythagorean theorem. So this would be 40,000 plus 90,000 equals y squared. So y squared is equal, if I add that up, to 130,000. So I'm going to need the square root to take the square root of 130,000. And I already kind of know who it is because of one number being bigger than the other. And this turns out to be 360.56 approximately here. Because again, it's an irrational number. It's going to go on forever, and this is in feet. So clearly, Kim walked the furthest away from the campsite, and if we want to know by how much, I'm going to just approximate by subtracting these two numbers. So I have 412.31 minus 360.56, and I get 51.75 feet further away. It didn't ask for that, I just threw that one in for free. So you can see that you're dealing with irrational numbers from time to time. So you're going to have to get used to it, and you can as long as you practice, practice, practice.